you. Hello, everyone. Hello, Sydney. What an amazing city you have. What an amazing country. And I hear everyone complains about the weather. But I must say that your winter feels like our fresh summer in Germany. So I really, really like it here. So today, I would like to talk about a topic which is partially serious and I hope partially is fun. We are going to build some dynamics AI-driven worlds for some practical use cases and fun use cases. And while doing this, we will look at different applications, research papers, and also we will look at the demo step by step, kind of using a number of technologies. So we will touch topics such as agent-based model. We will talk about retrieval-augmented generation. We will talk about event-driven systems, agents, and many, many other things. And while doing this, I would like to keep a focus on three pieces, three evolving different, the things which actually have been existing separately, but when we unite those, they become a very powerful backbone for our architectures. So this is the data streaming, data, and AI. And here, data streaming, we can think of it as a nervous system of our application where actually all the data moves in real time and enables all those powerful scenarios. Then AI is the brain of the whole thing, and data itself is like a memory, all those vector searches or data warehouses or everything, all of that together. So we will see how those unite in different use cases. So yes, I am Olena. I work at Confluent. Confluent was founded actually by original creators of Apache Kafka. So we will see Apache Kafka later also. And we know a lot how to stream, how to process and govern the data. But today we will step back and we will talk about a technology which actually appeared way before any of the LLM stuff popped up. And it's actually called agent-based model. And the first development of agent-based model actually is attributed to 1940s. So quite a lot of time ago. They didn't have computers as we know them right now. So actually they used a lot of like paper and some moving figures to simulate a model using agents. And because later we started using more powerful technology and we needed more computational resources, the whole agent-based model wasn't really in like very frequent usage till 1990s. But what it is? So this is definition from Wikipedia, not from ChatGPT. And agent-based model is more or less computational model to simulate different activities which we have using agents. And those agents can be some individual agents, but also can be some organizational groups. We can simulate the whole country. Depends on the size of the country. We can do it for Australia, I guess. Then we want to simulate the behaviors and we want to see what is happening with the system to come up with some conclusions. And for this, apart from LLM, which is emerging, there is a lot of different computational approaches I use. So we have the computational sociology, we have evolutionary programming, we generally like apply things like game systems and so on. Parts of so use cases which are quite frequently to generate with ABM is to simulate different scenarios. For example, when COVID came, ABM was used to simulate and see how the disease can spread. Then we can also see how different patterns and trends in society also evolve. Or if you have a team, or in general, like we can actually see what things make team more productive and which things make it less productive. We can apply it to urban planning, to simulate traffic conditions, to see where we put the trash cans so that people actually don't leave garbage on the street, and many other things, among which my favorite one and I found this in the list. So it was used to simulate, to kind of understand the consumer behavior by a dinosaur, which is called Allosauridae. I'm really bad with dinosaurs, but I think it's like a cool use case. They try to figure out the pattern in the food preferences of this dinosaur, how exactly what caused it, and was it the conscious decision of the dinosaur or just like pattern affecting effect from other animals which we live in at that age. So many different things. And when we are talking about building blocks for AVM, we have some obvious ones. We need agents, one or more. So those agents have their own attributes, behaviors. They need to be able to make decisions. We have also environment where those agents kind of live. This is a space where they operate and interact between each other. It can be a physical space. It should have some kind of external factors, or like depending on the use case we are trying to measure. This can be like weather condition or economical changes or political shifts, natural disaster, whatever we are trying to measure. So that's environment. And interactions can be direct from agent to agent, but then also can be agent with environment. And agents should have some autonomy, social ability, reactivity, so that they kind of can react to changes in the environment, but also proactivity, so that they kind of evolve, they change, they learn from the environment, and they do things differently based on the previous outcome. And all of that existed before large language models. And there were cool stuff built with that. However, large language models, it can add us some other new kind of like volumes of knowledge. And for example, it can increase the perception by the agents of the world around it. The decision making improves also with large language model comparing to how we were doing it before. Adaptive learning, and also it makes it easier for us to create more agents with kind of like a better ease, so we can generate more diverse characters with different abilities and different maybe behaviors, so that we create a more complex system. So all of that now opens a world for us to use both LLM and agents together to create cool things. So here I would like to move us and talk about some of the papers before we go into more like practical building of something together. I wanted to mention a couple of papers which give us good examples of what can be built and how those features can be used. So the first paper, and I'm not sure if anyone have heard about this paper before. It's called Generative Agents Interactive Simulacra of Human Behavior. Did anyone hear? No. This is like really cool paper. It's like 2 years old, but what they did, they created a really well-designed environment with a good variety of different agents. And they implemented a thinking process, which is quite an innovation, I think, to this day. And they simulated memory, observations, reflections, everything which actually helps to build up this self-reflection of an agent. Also, they added some interactions to create a common goal for some agents to achieve. So the whole village, or I call it a village, they probably call something else. The whole village has a lot of different areas. So we have houses, we have college where students study, we have some shops, cafes, bars, parks, where our agents can interact and meet. And those houses also inside, they do have some objects. For example, an agent can go open a fridge, take the meal, eat something, go to sleep, or go to use the bathroom or whatever. And those agents have their schedule, so more or less, like they have a routine, but they can think and change their mind. So they kind of like, if say nothing really influences them, then they just go with their schedule of the day. But if not, if they meet each other, if they kind of spread some ideas and they want to do something else, they kind of change their plan. So here we have like around 20 something those agents. They go around. The demo itself, so it's written in Python, and I could run it when it was released. But later when I tried, and I'm not a Python developer, all those versions in Python, God, it's like crazy. So, but they have a recorded version of the whole demo, and at the end I will leave you a link so that you can check it out. So, so we have those agents. We can check the information. So the information about their personality is kind of predefined. But then they kind of create the world around them. So there is this GitHub repository. All the code is there. Very cool to see how the prompts were designed. So this is 2 years old. So this is still with GPT 3.5, which was actually challenging because the context window was shorter. But the fact that context window was shorter also gave them extra kind of like they forced them to think how to store less memory, which is actually quite representative for a human being. So honestly, my memory is really flawed. Whenever I live in an apartment, I never remember if I close the door. I'm not sure if anyone can relate. Then I'm going a couple of blocks and I'm like, okay, wait a second. It really bothers me. So I have to come back to find that the door was closed. But I don't remember. And those things, some things are less important to remember than others. So they did a similar one. So they have this memory stream. And there is a lot of things happens with agents. Whenever they interact with some object, they actually kind of remember about that. We put it into the memory stream. But then when we need to define what is the next plan or what kind of to answer some questions, actually they take only some of the memories while leaving other behind. So we have those different formulas, or actually formula is one, to define what exactly an agent will be remembering. So here, for example, for Isabella, the question is, what are you looking forward to the most right now? And Isabella thinks that she is looking forward to Valentine's Day party that she is planning at Hope's Cafe. So there is a YouTube video with the creator of this paper, with a group of those researchers, and he explained how they made that formula. So this retrieval score, which they give to different memories, depends on how recent was that memory, how important and how relevant. So here they also use embedding and cosine similarity. So all those things. So in short, this is how it works. Agents, they perceive things around them, and that eventually should bring us into some kind of action. But before that, we put everything into the memory stream. We retrieve only what is needed. And then actually we do a couple of things with retrieved memories. Because this looks kind of like the basis of generative agent memory, but there is some important part which right now we see more and more with models, but at that point of time, that was kind of a new thing. So reflection. So from time to time, independently of what is happening, agents have this moment to reflect on what is happening around them and put more memories into the memory stream. And later, when they were evaluating the systems, they found that this reflection mode is very important to create in general, this self-aware agent. I don't know to which extent it's self-aware. The test they made, and I will show later, it shows that it's self-aware. I still doubt it, but anyway. So, and the same with planning. So, retrieved memories, they affect what agents plan. This is also affects how the kind of the flow of the day changes comparing to generally the schedule which they have in mind. So with example, for example, of Klaus Müller. So we have some observations, and here, for example, Klaus Müller is reading about urban design, from the bottom, right? Or Klaus Müller is discussing his research with librarian. But then there are from time to time we have reflections. For example, Klaus Müller spends many hours reading. And then it kind of bubbles up, and at the top we have that Klaus Müller is highly dedicated to research. So this is the picture of things within Klaus Müller memory stream. So it's kind of like he's kind of becomes more self-aware of what he's doing and why he's doing. Next, they try to evaluate the emergent social behaviors, and they did it this way. For some of the villagers, they will put in some seeds of some ideas. They did for Isabella, and Isabella, they put a seed of that she wants to organize a party, a Valentine's Day party. And then they observed, can she actually organize other villagers to make that party happen? Because you need to have guests, you need to bring some stuff, you kind of need to align everything. And she managed, so she talked to some of the villagers, not everyone, but in general, she reached over 50% of all the villagers, and some brought balloons, some just came to the party, some had to decline because they had other plans, but generally they considered it to be a success because she managed to spread the idea to other villagers. They also had the village mayor, anyway, like so the kind of election coming, and then they also saw how he can actually advertise for himself so that people vote. So all in all, when they measured this, and then I take everything related to AI with a grain of salt, but this is how it measures. So they put all that architecture with all the memory and all the ideation, and they compared different parts of it. So the full architecture or only parts of it, for example, without reflection and without plan, or like no reflection, plan, observation. And they also took a group of humans who kind of also interacted in a similar way. And they showed actually that the full architecture is more believable than the humans, crowd workers. For the evaluations, they also used humans, and we are flawed. But in any case, this is pretty cool paper. Again, I will take a grain of salt of trying to say that agents are more believable than humans. But who knows? Who knows? Because the next paper by kind of almost same group of researchers was actually closer to us. They try to now to really simulate a human. So imagine you come in a room as a human participant and you do a 2-hour interview. You answer some questions, very innocent, and then they create an agent based on your answers. And now they compare. So they kind of ask you a new set of questions. So like according to a lot of other social things, which I am not a social behavior scientist, I don't know, but there are like a lot of this big 5 personality inventory. So all those like economic games, there is also a research paper where they explain all those things. So they run those tests on both humans who gave interview and also created agents. And they showed that actually it's very accurately can simulate those humans. There is a GitHub repository with the code. They did interview like personal data apart from June Park, who is like the creator. So he also got the interview, but it's interesting concept. So technically we can simulate also like personalities. Now, on another side of things, sometimes we don't really need to simulate something in such a depth. Rather, we want to simulate more of the things. And for this, for example, in OpenCity paper, they actually simulated a place up to 10,000 people, agents, sorry, not people, where they try to simulate some urban scenarios. And here the challenge was generally is that, again, LLMs, they're evolving. Of course, we can make bigger and bigger requests right now. But once you try to simulate something like with 10,000 entities, it actually gets really complex. So they try to create this request scheduler to put together a lot of prompts together for similar activity, for similar agents, so that they save on the amount of prompts they need to do to LLMs. Anyway, it worked. So they created this group and they're still prompting. Pretty interesting approach if you have a lot of agents. Couple of other papers. This one from Microsoft. It's called a tiny troop, which has what they call a tiny world, and there is a tiny persons. And here, they actually have, they use it for kind of productivity and business scenarios where you want to give a task to a group of agents. Let's say you have 5 agents and you say, could you create an advertisement for something? And those agents then talk to each other. They also think, and they together brainstorm the best solution. So this particular, at least from the GitHub repository, and I will again leave all the links later for you, this kind of died out. So they created, I think maybe it was like a year ago, and never really continued working on that particular demo. However, at the end, I will show another Microsoft work, which I think is very close, but more for a targeted use case, where indeed we give a power to agents to brainstorm some questions and bring us solution after that. So while looking at all of those papers, I was also like, okay, I want to try things. So the first thing which I tried was like, how about we create a mafia game? Like, mafia, like you have one mafia and then you have villagers, and then like you see if mafia manages to kill villagers, so villagers win. Anyone played mafia game? They call it werewolf in Germany. But anyway, so I did that, and I also introduced like that they are kind of like Olivia, for example, tells something, and Vincent and David, they think what Olivia said so that they can make a better decision. At that point of time, to be honest, it was kind of a fail because there was a very strict correlation. Who starts the game? If it's mafia, mafia wins. If it's villagers, villagers win. So they were not super unique. But anyway, so that was the mafia experiment. Then I did another experiment because I'm a software engineer. So actually, I spent a lot of time with data streaming. So how about I will create a couple of agents which talk to each other. And here I was using a PubSub, a Kafka topic. Then they have reflections. Then every conversation then summarized. And it goes into vector store. And later when they start the conversation again and again, we kind of develop the whole new story. So it was about 2 aliens. So with that, now I wanted to show how we can build something a bit, this was so much into the terminal, and I wanted to have visuals for you and me to bring the data streaming with a bit more kind of a visual effect. So let's build a village. And now the most important question I have for this talk, how many of you played Stardew Valley? Okay, I see some hands. For those of you who haven't played Stardew Valley, please don't. You will save so much of your time. And I totally don't want to admit how many hours I spent on that. So we are going to take the game characters out of context. We will put them on the map and we will make them talk to each other. And while doing that, we are going to use my favorite set of technologies. We are going to use Apache Kafka. We are going to use Apache Flink. We are going to use an LLM. I used OpenAI. And we are going to use also Retrieval-Augmented Generation and vector search. So Stardew Valley was kind of an easy place to take stories of the villagers, so and bring them to code. So, for example, I took Louis. He is a mayor, so I just copy-pasted his background story to my project so that I don't have to invent characters. And then I also found a lot of sprites on the internet so that I can reuse them to make the characters walk on the map. And in general, the architecture looks like this. So it's essentially we have a villager. Then we have a world. And then, so I was using JavaScript. And then on the animation frame, we actually make the villager walk or change directions or like kind of imitate the game actually. Like during the festivals, they walk around, they pause, they talk to each other. So when it first, like, so they were walking, I was super, super happy that they managed to make them walk. That was probably the easiest part of the project. But yeah. So with that, Next, I wanted to make them talk. So for this, I wanted to make them to approach each other in real time. And when they're close enough, then they can make this decision whether they want to talk to each other. So for this, I needed some locations ongoing in real time to be sent somewhere so that I can calculate the distances between them. So I'm using here an Apache Kafka topic. So all the locations from the villagers come into Apache Kafka topic. Who's familiar with Apache Kafka? Okay, that's pretty cool. I think like we have almost everyone in the room raising their hands. For those who are not familiar, this is the most well-known distributed event streaming platform. And this brings data among different places, and whether you are connecting microservices or even like working with some agents, whatever you have, we can navigate the data very quickly with Apache Kafka. And in under 1 minute, because I don't have much time, how Apache Kafka works, it's like a pipe. You can make it bigger or smaller depending on how much data you have. We produce the data into what we call a topic, and then we consume the data. And if you have more data, you can add more producers and more consumers. If you have less data, you want to save those resources. You don't want to spend too much money on kind of running servers when you don't need them. And behind the topic, we have partitions so that the data can run in parallel. So this is kind of the basic, yeah, of course, we have replication. We kind of smartly can shut down some servers for maintenance. So a lot of kind of complexity behind Apache Kafka, but in principle, Apache Kafka is actually based on very straightforward concepts. So we send the data from our villagers into Apache Kafka topic. And this is kind of an object. Here I have Sam, I have the locations of Sam, and the timestamp when it all received. So actually, with Apache Kafka, the data later stays as long as I need it in the topic, so I can replay the whole movement of the villagers if I need to. Next step was to find when the villagers are close to each other so that we can start conversation. So we need to do a bit of math on all the villagers which are on the map. For this, I needed some kind of a computation engine which will be able to calculate the distances between all the villagers. And I used Apache Flink. How many of you had a chance to work or like to at least see some to know something about it? Oh, we have some hands. That's really nice. So Apache Flink sits at the heart of the real-time data platform, and it can work with different types of data. So we have this unbounded data as a data stream, like whatever like events you have coming to the system, or you can also work with some bounded data from the databases. And then you do some computations. Probably the most, like the example which I use for Uber here, whenever we are looking for the nearest car, the system can actually use the real-time data of all other cars around it, or like people who are looking for the car, but also look at the trends from the past week or like the traffic patterns and so on. So to combine both real-time data and historical data together to get you the best solution, like the best car which should pick up that passenger. So Flink is ideal for such use cases, and it's super scalable. But for us, we need to calculate the distance between villagers. And Flink you can use with SQL, with Python, with Java. I'm using here SQL, and generally I'm taking every 2 villagers, one direction only, and then I'm calculating the distance between them. And if the distance is less than, I have here 1024, this kind of like pixels in a way, then I define them close to each other. I compare them by name, again, one direction only, and I do this for every second. So every second I will output if they are close to each other or if they are not. And the data goes to a proximity topic of Apache Kafka. So for every villager, majority of course will be like farther apart from each other, but from time to time I will have them close. So here, for example, Jody and who was there, they are far apart. Robin and Sebastian also are not close. But from time to time, They come closer to each other. I'm not sure if it's visible, like I put the boxes around them so that they see when they should emit those events, they are close to each other. And when they're close to each other, we start conversation. For this, we're using a large language model, and I'm also using Kafka as a place where I store all those conversations, so all together, technically, again, replayable. And all those villagers then send the data into the topic, and I observe the topic, and whenever the message comes for a particular villager, I just kind of initiate that conversation. So, and they started talking way too much. It was like, yeah, let LLM talk, and you cannot really shut it down. So I had to play around so that they don't talk too much, because, for example, they finish conversation with one agent, start immediately with another one. So I had to kind of create this cooldown for several seconds between the conversation. Or if they were passing, like sometimes they go not so, like they kind of go around each other, and then I have to abort conversation so that they don't walk away and talk. Also, prompts was kind of an issue. Can be me, because I was a bit greedy and I used older models just to be able to send a lot of requests to LLM, and I was using older models to save money. But in any case, it started working. And all the conversations, as I said, again, like, so they are in the Apache Kafka topic. For example, here, Linus talks to Luis, something about Penny and Emily. Some more magic, I had to prevent cross-village conversation and to align them. And this is generally how the prompts look like. So the instructions will, I was given information about the character itself, also about the other character with whom they have a conversation. So everything which you can actually get from Stardew Valley website. And then I was very detailed, like only give a reply, no explanations or meta comments, do not mention your own name. So a lot of things which LLMs sometimes inject into the response. So that was iteration, and in the end, it was working pretty well. So now, when they were talking, it was like ongoing conversation, but it didn't go anywhere. I wanted to add a memory. And for memory, I wanted to use Retrieval-Augmented Generation so that we can have later a search across the memories for the most important things. And I guess, so Retrieval-Augmented Generation, Rag, how many of you had a chance to use it in practice? We have quite a lot of hands. Generally, Retrieval-Augmented Generation is very powerful to add extra context, and it's actually pretty simple. Whenever we are sending the request to an LLM, we just add extra context which we retrieve from a database. And we very often use vector search for that. So here, whenever the two villagers were finishing conversation, I was sending a request to an LLM to summarize their conversation. Then the response from LLM, that summary, I was creating a vector on that and storing it in a vector database. I used OpenSearch. And then later, when I had to, when the conversation was going, I was always referencing those memories to get something relevant from the previous conversations which were happening by this villager. And they started remembering stuff. So we started keeping like memories for those villagers. This is, by the way, how vector looks. So this is a summary of conversation, and the vector is like a lot of numbers there, which later we use for the search. One last thing, so like in the one of the papers I was showing, I wanted to give kind of a goal for the villagers. So for Jody, I introduced the goal that she wants to organize a conference, and I don't know how complex actually it is to organize a conference, but Jody took this initiative and she started convincing everyone and talking about the conference idea to other villagers. And she shared with Maru shared with Sebastian, Then Pierre learned about Conference, and yeah. And one last thing, because I know I'm running a bit out of time, what I wanted to leave you with. Now, even though I consider that Stardew Valley is the best example ever, I wanted to leave you with another example of using LLM for not exactly storytelling, but rather solving mysteries. This is based on the paper which I read a couple of weeks ago. And this is by Microsoft and their AI diagnostic orchestrator. Here we also have different roles. And here imagine that you actually want to investigate some kind of an illness in a hospital. And instead of taking a doctor, you actually take several agents. And those agents collaborate on finding out what is wrong with the patient. But you give different roles to the agent. For example, you have doctor hypothesis to figure out, to suggest what is the most probable cause of the illness. Another agent to choose tests. Some agents to challenge the assumptions and biases. Someone to decrease the price, or like to fight for the lower price, and someone to control that everything is going according to the plan. And you have that virtual doctor panel, which goes through the chain of debates, can do three things: ask a question, require a new test, or provide diagnosis. And at the end, you have a judge agent, which can show that if the diagnosis was correct or incorrect. And all of this can be compared to your normal doctor. So in this paper, and I kind of feel that this is still for me is very relevant to how we can use LLM to simulate things. I recommend reading the paper because it's super, super cool how they implemented it, but they benchmarked it on the set of agents and also on the real doctors. And a normal physician without access to internet can correctly solve 25% of cases, versus a panel of, or even AI, is up to 80%. The way how they implement it, I still believe in the doctors, honestly. But now I feel less guilty for asking ChatGPT and complaining about all my health problems. So this is kind of an interesting use case. Totally recommended to read it. The links to everything I showed you can find here. And for those of you who are who love Apache Kafka, we also have this test and certificate. It's like totally free, just actually for fun, which you can run and see how many questions about Apache Kafka you can answer correctly. Apache Kafka, Flink, and Iceberg there. So with this, thank you so much for listening to me.